All right, so if you could take your seats, we'll start the next session. So I'm Gaurav Sukhatme. I'll be chairing this session. And this is a session with 9 talks. These are the papers nominated for the various awards, the 3 awards that the conference gives out. We'll do these in sets of 3. The first 3 speakers are nominated for the Best Paper Award. We'll take questions after the 3 of them have given their spotlights, and then we'll do the next set of 3 and then the final set of 3. So the first speaker is Harold So, and he's going to talk, aptly enough, to follow Maya's talk about the transfer of human trust to robots.
Okay, so I'm going to share a little bit about our work in understanding and modeling human trust. So there's a person there, we'll call her Jane, and Jane trusts the robot to navigate around obstacles. But does trust also extend to different tasks? For example, following a person around, or maybe it doesn't. And we're interested in this question because trust affects how we interact with robots. And it would be nice if robots can also infer how we trust so that they can guide our interactions appropriately. We would like to avoid situations of under and over trust, which can have dangerous outcomes. For example, in 1923, the US Navy lost 7 ships because the captain undertrusted her automated navigation system. Fast forward to 2018, and we have people overtrusting their, self-driving cars, right? So to understand this a little bit better in a world where robots can perform multiple things, we conducted human subject experiments using 2 separate task domains. So over here, you see the household task with a fetch robot performing pick and place tasks as well as indoor navigation. Over here, you see the autonomous driving scenario. I don't have my own self-driving car, so we built one in VR. Here it's doing various road driving and parking maneuvers. So we brought people into the lab, and they would group these 12 tasks by similarity as well as perceived difficulty. After that, we would ask them, so hey, do you trust the robot to do these 3 different tasks here? And then we would show them the robot performing two of the other tasks. And in these 2 others, the robot would succeed to both times or fail both times. And then we would ask them again, so how do you trust the robot now? And so what did we learn? Well, let me summarize for you. First, if you trust the robot to do something like pick up an apple, you'll probably trust it to do something similar like pick up a can of beer, right? Rather than something very different over here. So the second thing is that when you see the robot do something, right, that affects your trust in not only that specific task, but also related tasks as well. Finally, trust transfer is a little bit asymmetric, and this makes sense once you think about it. If you believe the robot can do something very complex, very difficult, well, then it's more likely you trust it to do something simpler rather than the other way around. So what does it mean in the context of modeling trust? Well, there seems to be some sort of underlying structure to tasks, which we call similarity, and that seems to affect how trust evolves. So how can we formalize this concept in a computational model? Well, we're going to leverage vector task spaces, and we assume that the tasks all live in this space, and we can get to this space by projecting into it. So we take some description of the task. In that case, it's just a text description of the task. We convert it into some latent real vector. Now, depending on your text description, you're going to get a different point in this latent space. So these are the 12 tasks of our household domain. Now, you can model trust in an agent A at time t to do task X simply as a function over this latent space. You can then query the model and ask it, hey, how does Jane trust the robot to navigate while following a person? And the model spits out 0.64, saying not so much. But trust is not static, it evolves over time. So if Jane sees the robot successfully perform a task, say navigating around some obstacles, that's going to change the trust function via this function G, and now she believes the robot can do that. Similarly, if Jane sees the robot doing something badly, say in this case, completely failing to pick up this apple, she no longer thinks that the robot can help her make lemonade, for example. So in the paper, we discussed 2 different models on this general scheme. The first is a neural model, basically leveraging upon dot or inner product spaces, similar to recommendation systems. The second is a probabilistic model that arises from viewing trust formation as human function learning. The key difference is really in the flexibility of the trust updates. In the neural model, the trust updates are learned. The Gaussian process model basically says that, well, people are Bayesian, right? We update trust based on what we observe. So how do these models perform? Well, relative to existing models that just treat trust uniformly, our models perform better when predicting trust over unseen participants. But for the GP model, it's very important to model initial bias properly. We discussed this more in the paper by using pseudo-observations. Now, we perform a second experiment where we try to predict trust on unseen tasks. So this is slightly more difficult, where we're trying to basically test the generalizability of the projection function. And here again, you see the neural model and the pseudo-observation GP really outperform the other approaches. So here we took a first step towards understanding trust transfer between tasks, but the techniques developed basically using this, leveraging this latent task space, where we can use that to model trust transfer between different robots, as well as the same robot, but in different environments. So if you want to know more, come talk to me at the poster, check out our code, or send me an email. I'm going to trust you not to spam me. Thank you.
All right, so our second talk is on rigid body dynamics, and the talk will be given by Justin Carpentier.
Okay, thank you very much. So, hello everybody. I'm Justin Carpentier from last CNRS, and today I'm going to talk about the analytical derivatives of rigid body dynamics algorithm. So, rigid body dynamics algorithms are a very popular framework in robotics. It allows to compute in a very efficient way both the forward and inverse dynamics of rigid body systems. And these two functions are very fundamental for both the control and the simulation of our robots. So the main question is to know why rigid body dynamics algorithms are so efficient. So the first reason is that they are able to exploit the spatial algebra formalism, which allows to write in a very concise way the equation of motion within 6D vector. The other fundamental aspect of rigid body dynamics algorithm is their ability to exploit the sparsity which is induced by the kinematic tree. So having said that, it appears that now modern applications in robotics also require to be able to evaluate their partial derivatives. So to evaluate derivatives, there is two fundamental ways. So the one is the finite differences approaches, where we consider that the input functions are the black box functions, and by adding a small increment on the input variable, we are then able to get access to the derivatives. So it works for only input functions, but it's not so efficient, and it's also sensitive to rounding errors. So the second approach is automatic differentiation. In this context, we consider that we know exactly what are the derivatives of basic function, and by just applying the chain rule formula, we are then able to get access also to the derivatives. So there exists very efficient framework to evaluate these functions, and the main problem is that these frameworks are not really able to exploit the sparsity of the spatial algebra derivatives. So let me explain this point through this picture here. So what we can observe is a rigid body system evolving at a constant angular velocity, and what we know from our background in mechanics is that the time variation of its orientation matrix is governed by this equation here. And this equation is very fundamental in spatial algebra. And what we did in our work is precisely to exploit this, the same kind of operations to really be able to derive the rigid body dynamics algorithm. So here, this is an example of the recursive Newton-Euler algorithm that is very well known to compute the inverse dynamics. And so what we did in our work is that we apply the chain rule formula together with the derivatives that we have here to get a very efficient way to compute the partial derivatives. In the end, we obtain an algorithm which is very efficient with a minimal complexity of O and D, where N is the number of bodies and D is the depth of the kinetic tree, while the state of the art was in O(n) squared. So the second contribution of this work is to understand the link between forward and inverse dynamic derivatives. And the question is, do we need also to get rid of the same rule to get access to the forward dynamics derivatives? And the answer is not. What we can observe is that forward and inverse dynamics are two reciprocal functions. That means that their partial derivatives are linked together through a precise link, which is done through the inverse of the mass matrix. So a third contribution of this work is to propose an efficient way of computing this inverse of the mass matrix and to get access from the inverse dynamics derivatives to the forward dynamics ones. So the first contribution of this work is an efficient and open source implementation of all this algorithm. So we have called this framework Pinocchio, which is open source. It is written in C++ and comes with Python bindings for efficient code prototyping. So feel free to use this framework during your own research, and you can get access to this framework through this GitHub webpage. So now it's time for me just to show you some results of this algorithm applied on several systems. So for instance, here we have a KUKA arm robot, and what we can observe is that in less 1 microsecond, we can compute the inverse dynamics, and it requires only 3 microseconds to also get access to its analytical derivatives, while finite differences are around 20 microseconds. So we can have similar observation of forward dynamics. And we apply that also on IQ robot, for instance, which is a 18 degrees of freedom robot. So in less than 7 microseconds, we can get access to the analytical derivatives. And the same thing applied for the Atlas robot, which will appear here. So in less than 60 microseconds, we have all the derivatives of the system, forward and inverse. So while it requires more than 400 microseconds to get them by finite differences. So now it's just time for me just to resume and to summarize the contribution of this paper. So we have 4 contributions. So the first one, an efficient way to get both forward and inverse dynamics of a system. A second contribution concerns the analytical inverse algorithm to compute the mathematic inverse. And then it's an open source and efficient implementation of all of this work. So we expect a very a large impact in preview control, for instance, on complex robots, in co-design, optimal estimation, and of course, policy learning. So I want to thank you, all of you, and I will be happy to answer your questions during the poster session. Thank you.
All right, and our next speaker is going to talk about manipulation planning, and the speaker is Marc Toussaint.
So hi, it's my pleasure to present this work on manipulation planning. We're generally interested in physical reasoning, as you might want to use it to do better perception, to solve 3D games, or as this animal right here might use it to retrieve the nut with a sequence of using tools. And down in the bottom, you saw our method. So to be concrete, the problem setting we're using is a planning problem. We assume full state information in terms of the geometries and scene description given, but no semantics of the objects, no notion of a hook or anything like that. Equally, the goal is specified as an arbitrary equality or inequality constraint on the final configuration, such as 0 distance between touching the red ball or the blue ball must touch the green target area. Now, how could you approach such kind of problems? Differentiable physics is a really interesting idea. It basically means that you could take any objective function over the future and compute the partial derivatives with respect to any input or parameter of a differentiable physical simulator. So that's a very powerful idea, but in terms of manipulation, the question is, well, the gradient is very often 0 if the contexts are not already there. We believe that gradients alone are not the answer to solve these kinds of problems. We need a better and deeper understanding of what actually the structure of these problems is. If you would then smooth the context, well, you would end up with a combinatorics of local optima in these optimization problems. And we think it's exactly that combinatorics of local optima that we need to understand and formalize. So our formalization starts with formalizing a general path optimization problem. Here, the path refers to all objects in the scene and the robot jointly. We have a standard control costs. We have the goal constraints, as I mentioned them. And then there is the physics constraints, which simply says the path must be physically feasible. Well, that implies all the complexity and combinatorics that I just mentioned. So it is this point, this green area, where we replace, make stronger assumptions, namely that we assume that the path is a sequence of modes. Mode meaning that a certain object might be flying around freely, or another object might be rolling on the floor, another object might be stably in the hand. And every mode per object defines a differentiable constraint on the path for that specific object. Now, on top of that, we introduce a logic. And the logic is kind of orchestrating the modes per object. The logic is saying, you're flying here, and you ball, you're rolling here, and then you two shall collide, and there shall be an impulse exchange equation for you two guys. So the logic kind of triggers which kind of differential constraints we have in the path optimization problem. Very briefly, these are the predicates that we use to refer to modes, and they directly relate to differential equations per object, like impulse exchange or the Euler-Lagrange equations. And we introduce strips rules, literally, to define the sequence of possible modes per object. That bridges to AI planning and eventually defines the decision tree of that AI planning problem. And we use a solver that we've published previously, which is very similar to branch and bound methods in mixed integer programming. It though uses actually a hierarchy of bounds of different computational complexity. Some results. We tested on 6 problems. The first example I give here is a typical dynamic interaction where the robot optimally grasps for the blue ball, throws it up, picks up the stick, kicks it so that the blue ball ends up in a green target area. Second example is in analogy to the bird retrieving the nut with a double hook So it's taking one hook to get the second hook, taking the second hook to retrieve the ball, and then got the ball in the hand. When you do the experiments, what is really exciting is that the algorithm actually not only produces a single solution, but a whole variety of solutions defined by that logical tree, by the possible sequences of modes. If you look in the top right corner, the solution that the robot found here is to grasp the hook, hand it over to the left hand, turn it away that it can kick the ball from behind, and then retrieve the ball with the hand. I haven't conceived of this solution before, but just by exploring the full variety of possible mode sequences, the algorithm found this. The running time to compute all of these varieties is between 20 and 200 seconds. More details at the poster. We also did experiments with humans and analyzed whether the mode sequences kind of compare to what our algorithm proposes. They kind of do, but frankly, we also found a lot of limitations of our method that do not match up to what humans actually do. Let me conclude saying that this work very much tries to integrate ideas from many, many different areas. So if you're a researcher into task and motion planning, I would hope that you're interested in our method because we're using optimization to get physics into TAMP methods. If you're a person into hybrid control, well, essentially what we're trying to do is bridge between control and AI planning. And we do so by introducing special kind of logic to define mode sequences. If you're into contact invariant optimization, differential physics, you could think of our work actually as introducing a logic of local optima. And I think it's very important to address this because, well, otherwise graded methods get stuck. And if you're into dexterous robot manipulation, well, essentially, I was trying to understand your ideas and concepts of stable pushes and stable graphs and translate them to AI plannable representations. Thank you.
All right, Mark, don't go far. So you could give up your mic and come right back. So I'd like the first three speakers to join me on the stage. We'll do a question session. And it's crucially important that the next three speakers use this time to get mic'd up. So if you're in the next set, please be mic'd up. I think the colored boxes are on their way. Excellent. Who would like to ask the first question? We have one back there.
Hello. So this is a question for the second speaker. Can you speak to any limitations of what type of dynamic systems you can handle with this method? For example, can you handle systems with closed chains or other kinds of constraints? What about under-actuated systems?
Okay, for closed chain, not currently. So we are developing the derivative for this algorithm. There is already some works on that by Frank Park, for instance, in 10 years ago. Almost. So we can handle, of course, under-actuated systems, so like IQ or Atlas, for instance. So, and current work is to derive also second-order derivatives and so on. So, yeah, there is still some work in progress for improving all the framework and to get very fast access to all this information, which are crucial, for instance, for optimization in general.
Hi, my question is for Mark. I really like the manipulation, the examples, the multi-step tasks. I was just curious, these are precise tasks that would have to deal with some uncertainty, and in stochastic settings, like, does this method sort of fit well in those domains, in those settings where there's a lot of uncertainty?
So the planner is assuming a completely deterministic world. And you see this sometimes that it's creating plans which are very unlikable. For instance, sometimes it's throwing a block to hit another ball from behind to actually go there, which is like playing billiards, but completely unrealistic that it could do that. So answer is no, that this method right now assumes a deterministic world. We're thinking about extending it to stochastic domains. And in particular, we're also thinking about adding a stochastic layer on top of that, which then does reinforcement learning to check if these plans are actually executable when trying to execute them in the real world.
There's a question in the front row.
So there's another question for Mark. You're relying on these logical predicates that basically are defining the parts of the configuration space where the dynamics are smooth. Is it easy to know when you have exactly the right set of predicates? Is it possible that you might be missing some, or what is the relationship between the underlying physics, which presumably specified by like a URDF, I guess, and the completeness of the problem?
Yeah, that's a great question. First, I think there's two philosophies about the predicates to define modes. The one philosophy would be, I want to find like the minimal and most general set of predicates and modes that describes all of physics. And there we would actually go down maybe to control theory, and the modes would really correspond to contact modes, and that would be a minimal set of modes. Although another philosophy is to say that I want to include modes which introduce more higher level abstractions of sensible manipulations, such as stable pushes, stable graphs. And then it becomes more a matter of, well, how much understanding do I integrate from the people that actually work on dexterous manipulation and translate them into a set of modes. I can't really say what the ultimate set of modes really is for that.
Right.
So a question on the analytical derivatives of the dynamics function. How did you evaluate the results? Did you compare against what finite differences would tell you, or did you use them for actual control tasks? How did you evaluate the quality of the results that you get?
So currently, we just provide some evaluation against finite differences. We compare also against other frameworks that provide them by automatic differentiation. So if we compare to that result, for instance, we are already much more faster, while we don't have, for instance, code generation that other framework provides, for instance. So the aim of this work now is also to go a bit further and to control directly with these equations the motion of leg robots mainly. So using, for instance, optimal control theory for doing that. Yeah.
Any other questions?
That's a question for the second speaker. So how much of this work actually carries over for the case of stochastic mechanics? If you have stochastic forces, some stochasticity.
I don't know the answer. I don't have any answer for this question. Maybe we can discuss it later to explain me what do you mean by all these things.
So because you mentioned that, you see applications on estimation, right?
Okay.
Then, in estimation, you will have to consider stochastic differential equations.
Yeah.
So I was wondering.
Okay, yeah. For instance, in this case, so just an ambition to use this framework for that, but for instance, doing optimal estimation using differential dynamic programming, this is the main target. But using, for instance, now the whole body equations and not solely just a radius dynamics like the centroidal dynamics or other stuff like that. So maybe, I don't know if it's answering your question.
We can talk offline.
Okay, yeah, thank you.
All right, so I think we'll move to the next set of 3 speakers. Let's thank these speakers again. Thank you. Right, so the next 3 talks are on papers that are nominated for the Best Student Paper Award. And the first talk is on a generalized Dubbins interval problem given by Petr Vanya.
Hello, I'm Petr Vanya from Czech Technical University in Prague, and I would like to talk about path planning for area vehicles. Our work is motivated by a surveillance mission in which a fixed-wing vehicle with a limited turning radius is requested to collect data from the given set of sensing locations. We formulate this problem as a Dubbins traveling assessment problem with neighborhoods because instead of visiting the locations precisely, we allow to use a sensing radius to collect them from the vicinity. To address the non-holonomic constraints, we use classical Dubbins vehicle model, and the optimal solution between 2 states is known for decades. But here, the goal is to find a visiting location in which the data is collected. For that, many approaches has been proposed in last 2 decades, but most of them are only heuristics. So we want to find the optimal solution, and there are several ways how to do that. First, we can use convex optimization, but we are able to do that only if the sensing locations are far enough, which is not our case. And to find the optimal solution, or at least bound the solution's quality, we used relatively recently introduced so-called Dubbins interval problem. It is an extension of classical Dubbins maneuver, where the heading angles are selected from 2 angle intervals, as you can see on the image. So we aim to find the shortest maneuver between these 2 intervals. And thanks to that, we are able to bound the lower bound of the Dubbins traveling salesman problem, but in this case, without any neighborhood, because it's from point A to point B. And to have a neighborhood around the sensing location, we used disk-shaped regions around the locations, and so we introduced generalized Dubbins interval problem. The main observation here is that this problem can be transformed to its one-side version, where the first region is collapsed to a single point, and the second region is given by a Minkowski sum of these 2 original regions. So it reduces the configuration space and helps us to find the optimal solution. The proof is provided in the paper. And then we identified 7 different maneuver types. And for 6 of them, we were able to find a closed form solution. But for the last, we weren't. So we transformed the last case to a convex optimization problem. And the good property here is that all of these 7 maneuver types can be solved in about 13 microseconds. And thanks to that, we can lower bound the Dubbins traveling salesman problem with neighborhood. And here is an example for fixed sequence of the visits. You can see the red line here is a lower bound path, which is discontinued because it's not feasible, and the blue line is a feasible solution. And while the resolution is increasing, you can see that the red line and blue line is converging together. And after, let's say, 33 seconds, you are 1.3, I think, % from the optimal solution. So you can guarantee it. And I want to conclude that in this paper, we have introduced generalized Dubbins interval problem, provide optimal solution for it, and also show how it can be used for solving Dubbins traveling salesman problem with neighborhoods and provide a tight lower bound for this problem. An interesting property here, if you know the sequence, the computational time scales linearly with the number of regions. So thank you for your attention, and please come to see my poster.
All right, so our next speaker will tell us some new results about in-hand manipulation, and his name is Nikhil Dafle.
Good afternoon, all. My name is Nikhil. Today, I'm presenting an in-hand manipulation approach that exploits the reachability knowledge from the mechanics of pushing. It's not always possible to pick up an object in a pose that is immediately useful. We want robots, even those with simple grippers like this, to regrasp an object in hand by using the environment. So we have developed a framework that allows the robot to push against the environment and regrasp the object in hand. So given an initial grasp and a goal grasp, we want a robot to come up with a sequence of pushes that forces the object to the goal pose. One of the key challenges when planning such pushing strategies is to characterize which object motions are feasible, given the dynamics of friction contacts. In our work, we show that it's possible to estimate the set of feasible motions or the set of reachable configurations in the form of a motion cone. Using motion cones as reachability bounds directly in the configuration space, we developed fast and efficient in-hand manipulation planner. A variant of motion cone was introduced by Matt Mason for the case of pushing an object in a horizontal plane with a point pusher. There, a motion cone is a set of motion twists that a pusher can impose on the object using frictional contact. In our work, we extend this idea to general set of pushing tasks where external forces can alter the dynamics of pushing. For example, when pushing an object on an inclined plane or in a grasp, not only the pushing force, but also the gravitational force has an influence on the object motion. And we would like to capture all those effects. In our paper, we present an analytical approach to compute motion cones. Here, I'll present a graphical intuition. So let's consider a representative example. An object in a parallel jaw grasp is pushed by a line pusher. The configuration space is three-dimensional, since the object can translate in xz plane and rotate about the y-axis. We model the force-motion relationship at finger contacts using a limit surface, which is the integration of all frictional wrenches over the finger contact area. For an external wrench on the boundary of the limit surface, the object will start slipping at the finger contacts, and the direction of slipping will be given by normal to the limit surface. When we consider the combination of all possible wrenches from the pusher and the gravitational force and intersect it with the limit surface, we get the set of finger wrenches for possible object motions. When we draw normal to that intersection, we get the set of object motions that the pusher can impose using the frictional contact. This set is a cone defined by low curvature surfaces, and this is the motion cone. Any object motion inside the motion cone respects the dynamics of pushing. Motion cones in general abstract the dynamics of contact-based manipulation and can be used for simulation, planning, and control. In this paper, we explore their application for planning in-hand manipulations in a sampling-based planning framework. Specifically, we use the knowledge of these feasibility bounds or reachability bounds from the motion cones to grow an exploration tree. So instead of solving for the complex dynamics of pushing, we project the sample configurations on the motion cones and grow the tree via motion cones. A path in this tree provides us a pushing strategy to force the object from a start configuration to the goal configuration, while going through the grasp configurations that are dynamically feasible. Here are some regrasp strategies generated by our planner. The planner took a fraction of a second to generate these strategies while doing online computation of motion cones. So this is an order of magnitude faster than our prior work, where we explicitly solve for friction dynamics or the pushing dynamics at every instance. Moreover, because motion cones provide the knowledge of set of all possible actions that we can do, the planner exploits that knowledge to take more direct strategies towards the goal. We believe that using motion cones as reachability regions directly in the configuration space is a very powerful idea for contact-based manipulations. This reachability knowledge opens a window to see the connectivity in the configuration space and use it for fast and efficient planning and control. I'll be happy to see you at the poster and discuss this work more. Thank you.
All right, our next speaker is Alex Zhu, and he's going to talk about flow estimation for event cameras.
Hi, everyone. My name is Alex, and today I'll be talking about a neural network approach for optical flow estimation from event-based cameras without any ground truth labels. So first, what's an event-based camera? Basically, they are asynchronous sensors that detect changes in log light intensity. What this means is that whenever the log intensity over any pixel changes over a given threshold, the camera will immediately return the XY position of the change, a timestamp accurate down to microseconds, and a polarity, which is whether the intensity went up or down. So on the slide, we have some sample output from the camera when we're recording a fidget spinner spinning at around 40 radians per second. And here, the grayscale image is basically that white circle that you see. So these cameras allow us to detect very fast motions with very low latency. They also have very high dynamic range, and so work in a number of challenging lighting environments. And they also have relatively low power consumption compared to traditional cameras. However, with this new type of data input, we require a new sensing model. since we can no longer rely on traditional concepts such as photo consistency. This requires expensive algorithm development, with many traditional problems, such as dense optical flow, still proving challenging. This seems like a suitable task for model-free methods, such as neural networks. However, we don't really have that much labeled training data for supervised methods for the time being. In this work, we propose a solution to both of these problems by performing self-supervised learning using the grayscale frames that also come from some event-based cameras. So the first part of our framework is an input representation. Our contributions, I should summarize first, is the first CNN approach for event-based cameras to predict optical flow using a self-supervised method from the grayscale frames from the same camera. We also provide a new data set with ground truth optical flow for event-based cameras. So here we have some sample output from our camera and our method, where once again we have a fidget spinner spinning. And you can see it works for very fast motions and also in challenging lighting conditions, even when we occlude half of the light coming into the scene. In addition here, the color is the direction of the optical flow. So the first part of our framework is an input representation that converts the input stream of events into a 4-channel image suitable for a CNN. The first 2 channels of this image are the number of positive and negative events at each pixel, and the last 2 channels are the timestamps of the last event at each pixel, at each polarity. The timestamps here encode some kind of motion information in the scene, where you can see in each timestamp image that the gradient inside this image follows the direction of the motion. The event count images, on the other hand, provide us with a weighting of each pixel, so that pixels which are mostly noise and so generate fewer events have a lower weighting inside this image. And this provides the network information about which of the timestamps to actually trust when it's computing optical flow. We pass this input representation into a neural network, which consists of a standard encoder-decoder architecture with skip connections and a multi-scale loss. For an input image of 256 by 256 pixels, our network runs in about 48 milliseconds on a standard laptop-grade GPU and can run much faster with a much higher-grade GPU. At training time, we apply supervision using the grayscale frames that come from some event cameras, such as the Davis. This allows us to apply a photometric loss by taking the next grayscale frame from the camera and warping it to the time of the previous frame using the output optical flow from the network. We then apply a loss on the difference in the image intensities between these 2 frames, which we found that when we combine this with a spatial smoothness term on the optical flow, allows our network to learn optical flow without any other kinds of supervision, such as ground truth labels. For evaluation, we generated a new ground truth optical flow dataset from the multi-vehicle stereo event camera dataset, where we used the provided ground truth poses and depths. We trained our network on events and grayscale images from driving sequences from this dataset and tested on separate driving and flying sequences. The ground truth optical flow is also available online at the link on the slide. And here we have some sample outputs from the optical flow, where once again, the color here is the direction of the optical flow. We compare our method against Unflow, which is a self-supervised image-based method. We found that we mostly do better when the input images are 4 frames apart and so have a larger amount of motion. However, we did find that we tend to do a little bit worse when the input frames or input images are only 1 frame apart and so have a smaller amount of motion and generate fewer events. Here we have some qualitative results from our method on one of the outdoor driving sequences, where once again, the color here is the direction of the flow. As you can see, our network is able to predict accurate optical flow for every single pixel that has an event We found that once we trained our network, it was able to generalize to a variety of very challenging speeds, lighting environments, and scenes. We hope that this will provide not only a framework for self-supervised optical flow estimation, but also the transfer of other self-supervised methods from images to events. Please come to our poster, where we're going to have a live demo of this method in action.
All right, so I'd like the speakers to, for 4, 5, 6 to come up and take questions once they've handed over their mics. All right. We're open for questions.
I have a question for the first speaker. I wonder if you considered a more general setting where you need to cover a certain area and the neighborhoods are not given in advance. So do you think you can extend your work to such cases?
You mean if the areas are not given a priori known?
Yeah, you're given an area, specific area that you need to cover without those neighborhoods in advance. And you need to compute the neighborhoods so that you achieve some sort of optimality in terms of coverage.
It would be really nice to have this property, but right now I'm not sure how to do that because it's much more coverage problem and you would need many neighborhoods to cover the space, but I would consider it in future work. Thank you.
First row.
Also a question for Peter. The complexity bound that you gave at the end of your talk indicated it was big O of n to the k to 1.8. And that was kind of surprising because the outer loop is a TSP, right? And so I couldn't tell, is that the bound of the entire solution? If so, how do you get k to the 1.8? Or is that just the one iteration of the TSP?
In just one iteration, it was for the fixed sequence. So it's just the property if the sequence is known. And for the whole TSP, you can transform it to generalized TSP.
Okay, great. So can you use sort of approximate techniques for solving that outer loop TSP, like 2-opt or something like that?
Yeah, you can, but we want to find solutions very close to the optimum. So it's not a good idea to use 2-opt heuristics.
This is for Nikhil. What if you had the 3-finger hand? I suppose the 3rd finger can be used in the same way that you're using the environment. Do you see what you're doing?
So the framework can directly extend to those cases but in those cases, instead of having this single finger limit surface, you'll have grasp limit surface. So it will be the convex hull of 3 contacts if you have. As long as it's quadratic, you will get a guaranteed single solution.
Sorry, I have a question for Alex. So what's the difference you see for event-based camera optical flow and a traditional image-based optical flow? Or what's the challenge?
Okay, so the difference is first, a lot of the benefits come directly from the camera itself. Basically, since you get such fine-grained temporal information, you're able to track much faster motions. For example, the fidget spinner, on a standard camera, you're not going to see the actual rotation of the object. The challenges from the events comes from the fact that your input is now essentially 3D because it's spatial temporal. So how to actually decipher this information and turn it into optical flow is still an ongoing problem, which we're trying to model with a neural network.
All right, so I think in the interest of time, we'll move to the next three talks. Thank you very much. So our next speaker is Girish Chaudhary, and this is going to be a bit of a show and tell along with the video.
So hi everyone, I'm Girish, and I'm here to talk about TerraSentia. That's our robot that we've 3D printed, and I'm here to tell you why we did it, how we did it, and what it means for agriculture. And this work is joint with Erkan and Zhong, who are here helping me with the robot. So did you know that corn, as we know it, did not exist in nature, right? It was bred by our ancestors over a process of selective breeding for the past 9,000 years. In fact, most of the produce we eat today is being continuously improved through selective breeding. But right now, there is a need to improve that breeding process, because in Africa, the population is about to double in the next 30 years, but the yields are only 1/4 of what they could be. Modern breeders are using what are called as phenotypes that are traits, and they're trying to correlate these traits back to genotypes and then encourage those specific genes to come up with the next generation of crops. In order to do this, they run massive trials over hundreds of acres with thousands of cultivars. They're trying to pinpoint the plants that are performing the best. But the lack of automation in making those measurements is a bottleneck to their progress. For example, consider this guy counting plants in a field. It's an annoying job, and it takes quite a while. Systems like this gantry system can do this for you, but they're extremely expensive. Drones can't see under the canopy, so they're not as practical for this. So breeders asked us, can you build us a robot that can go under the plant canopy and count plants for us and do other things. But this is hard because the scales are vast. The data is very noisy, and the robot has to stay within the narrow 70-centimeter wide rows in the field autonomously. So our main contribution in this paper is this robotic system, TerraSentia, that can stay autonomously within the 70-centimeter rows of corn and sorghum. It's compact and lightweight, which makes it very easy to use, and we taught it to count corn using deep learning. Now I'll explain to you how we did some of those things. So the models we use for non-holonomic robots typically don't assume wheel slip. But on muddy days like this, the robot wheels slip quite a bit. And because of that slippage, you get a lot of loss of track, a lot of accuracy. So we introduced mu and kappa, forward and rotational traction coefficients, and created an adaptive controller that is capable of adapting to those traction coefficients using readings from gyro, GPS, and encoders. This system can estimate the vehicle states as well as the traction coefficients and generate the control. And it's highly generalizable to different types of sensors and different types of vehicles. Through field testing, we're able to show that this system can reliably report tracking errors less than 10 centimeters. That's really low for a GPS-based encoder. And it can meet rotational constraints and start off track. In order to count the plants, we use the sideward-facing camera and deep learning. But the challenge with deep learning is that you need a lot of data. Unfortunately, there aren't a lot of nicely labeled data sets with corn in there. So we used a transfer learning method that used the features from a convolutional neural network to train the robot to detect corn. Our method was able to detect corn with about 300 images. The next challenge was to deal with changing plant spacing. It's not enough to assume that within a window there is a single plant. So we use the camera motion to detect how many plants are passing as the robot traverses through the field. This results in a very robust system that can count plants with different plant spacing at different growth stages, with different lighting conditions, and at different speeds. In this last video here, the robot's driving about 1 mile an hour counting corn, this one here. And that's about 10 times faster than a human can do it. It's also fairly comparable with a human. In fact, breeders told us that they prefer the robotic measurements more because the robot can actually autonomously measure the whole field, as opposed to humans practically can only measure a part of the field and then generalize to the rest. So when we showed this robot to breeders, they said, well, when can we get one? So we went beyond just a demonstration and used the 3D printing techniques that we have written about in our paper to make 30 of these robots. So right now, across the country, there are more than 30 of these robots in fields helping measure plants and do other phenotypic tasks. So we think that these types of robots spell an exciting future for agriculture. Thanks.
Great. Our next speaker is Nils Knapp, telling us about how to modify unstructured environments.
Good afternoon. So I'd like to point out that the two students who did most of the work are here, so if you have really nitpicky questions, please come to our poster. So we want to build robots that operate reliably in these highly unstructured and highly irregular environments, like this area after an earthquake. And we think of mobility as one of the basic functions of a robot. So we designed a system that is able to modify the environment to provide navigability for itself and possibly other agents that share the operating space. So we think of navigability as a property of the environment, and then have the robot iteratively go through and change the environment reactively in order to provide a series of navigable points to an externally given target location. We proved correctness of this algorithm by coming up with a pretty abstracted version of the problem. And correctness here means that when the system finishes, that you're guaranteed that there's a navigable sequence of points in the environment to let robots get to this externally given goal. There are three things that are really important in designing this abstracted version. One is the representation of the environment. The other one is how to actually formulate navigability for robots in general, and then the material and the modification that you use for the system. So we used continuous height functions h to describe the state of the world, and that allows us to express really irregular features because we're not really stuck with any sort of discretization artifacts from the description of the system. We think of navigability as having 3 parameters. So for every robot, we imagine that there is a maximum slope kappa that the robot can go up. There is a discontinuity epsilon that most robots can just drive over without really caring. And then there's a characteristic length delta that describes how closely spaced these discontinuities can be. And that gives a really nice definition of navigability. So that's shown in the bottom. And it basically means that a height function is navigable when it is really close to a Lipschitz continuous function. And the way to imagine this is that you give me a robot, and I can determine these parameters. So if a height function is navigable by those parameters, then the robot can actually drive over it. The simple model also works in 3D. So this is the neighborhood of a specific point P, and it's the height function in that neighborhood. And you can visualize whether or not that particular point is navigable by sort of drawing a cone at that location. And if any of the height functions sort of stick out over the cone, then that point pair is too high and violates that specific condition. So we took all these definitions together and came up with this iterative modification algorithm. So this is a simulated disaster area. There is a target location, and we split the space into a navigable region and a reachable region, which basically means that the robot can drive to some navigable point and reach there. We pick the closest point in the navigable region to the target location and draw a line, and then check along that line whether or not all those points are navigable by those parameters. And if some points are not navigable, we look for the points that are in the reachable region of the robot, and then the robot modifies that particular point. And it just keeps doing that, and then you're guaranteed to eventually provide a path to this target location. There are a number of sort of specific design features of the system to actually apply this to a real-world robot. Mostly they're related to the material deposition. So we use these compliant bags because they both allow us to build on really irregular terrain, because these bags actually naturally conform to whatever you put them on, so you can build in really messy environments. And they're also pretty easy to manipulate, so we can have a robot that just has this like simple pinch gripper. The other part that we found is very important is to have suspension in the robot, because we want the robot to actually interact with the environment as it's being built, and we want it to be able to go over pretty large discontinuities. Right now, there's external perception, but in future versions of the system, we would like to onboard that. So in the video you're about to see, the target location is in the green area. The robot, once it determines that there is a point that it needs to modify, goes through this, out in the terrain, looks for these compliant pockets, and then places them on that irregular terrain. So the system ends up being really robust. So we placed many hundreds of bags over many hours, and the system can even recover from sort of faults if you disturb the process. And the reason that it's robust is that we're able to come up with this sort of abstraction that allows us to prove correctness of this algorithm. And we made all the pieces of this abstraction such that they're easy to map back onto a physical platform. And if you have any questions, please come and speak to us at our poster. Thank you.
All right, and the final talk of the session is on Agile autonomous driving, and our speaker is Yunpeng Pan.
All right, thank you. So in this work, we introduce an imitation learning system for high-speed autonomous driving. We focus on learning control policies from data. More precisely, we want to learn a function approximator that maps sensor input to action. The benefit includes lower cost, more flexibility, and the potential to improve performance over handcrafted method. In general, there are 2 ways to learn the policy. One way is reinforcement learning. We can do trial and error, but it is not sample efficient. Another way is imitation learning. In this case, we want to achieve an expert's performance. It is more efficient, but an expert is required to perform the task. In some cases, we do have access to the expert. For example, a human driver. Self-driving car is an example of application of imitation learning. In this case, the car can be controlled by a neural network that was trained using human driving data. But there are still challenges. For example, if we have a human driver drive the car around this track, collect the data, train the policy, this is called batch supervised learning. Because the data will not cover the whole track, when we execute the learner's policy, the car may go to places where we don't have training data, and collision may happen. And it has been shown that, in theory, the batch supervised learning could lead to a compounding error over time. A theoretically appealing way to avoid this issue is online learning. In online learning, we do batch learning first to get the initial policy. Then we use this policy to collect more data. And we use the expert to annotate the data. And we train the learner on the aggregated data set. So this is one iteration of online learning. And we can do it for many iterations. And it has been shown that online learning could reduce the compounding error over time. And so we want to build a system for autonomous driving based on this idea. Our task is to drive the car along this third track at high speed without crashing. We want to learn both steering and throttle command, and we want to learn the policy end-to-end from sensor data to control. But this task is not easy because the dynamics of the vehicle can be very complex at high speed, and the decision needs to be made at high frequency. So in our system, the learner is a neural network that takes an image and the wheel speed as input. In order to train it, we designed an algorithmic expert that consists of several modules, including state estimation and model predictive control. The expert has access to more advanced sensors, such as GPS and IMU. During the training phase, we have the learner, we have the expert, and we also have a safety controller to prevent high-speed crashing. During testing time, we no longer need the expert, so the learner only has access to low-cost sensors. After 3 iterations of online learning, we were able to obtain a policy that could perform high-speed, stable driving. In this video, the car was controlled by a neural network, and it only has access to a single camera and wheel speed sensors. In this video, we're showing that a camera video recording during training and testing time. And you can see that the learned policy is robust to minor changes in the environment. And we also compare the performance of online learning and batch learning. And we found that the performance of online learning is better than batch learning. In addition, we analyzed the generalizability of the trained neural network by embedding features in low-dimensional spaces. And we found that the policy trained using online learning is able to map training and testing data to a similar feature distribution. To summarize, we built an imitation learning system for high-speed autonomous driving, and we provide real-world demonstration of imitation learning theory. Thanks.
All right, so I'd ask the last 3 speakers to please come up.
Thank you.
All right, we're open for questions. Yes, there's one over here. So it's the orange mic.
Oh, great. I have a question for the second speaker about the red bags in the terrain. I'm curious if you were to use other objects that you found in the environment instead of the red bags, how much more difficult that would be.
So I think that's an excellent question. So we have some ongoing work where we want to use more efficient objects that are larger and can take up more volume. That's pretty easy. Ideally, this would go in the direction where you just pick up the objects that you find and rearrange them. But then sort of the rigid body stable stacking is pretty challenging to do. We have a little bit of preliminary work on that. But certainly that's the right direction to go in. Thank you.
Thank you.
Hi, this is for the first speaker. We 3D printed robot that was very neat. I'm curious if you could expand a bit on the 3D printing aspect of it. It seems like for driving in that terrain, having wheels with tires would be very helpful. So what are the reasons behind 3D printing?
Yeah, that's actually a very good question. So that's how we started actually with tires, rubber tires. But we found that with rubber tires, what ends up happening is that if a plant leaf gets stuck under the tire, it pulls the whole plant in. Instead, so that's why we created these new wheels, which will remind you of some lawn, the lawn watering robots. They have wheels like this. They actually cut the plant, so it doesn't permanently hurt the plant. And the other aspect of 3D printing is that it enabled us to try out a number of different design decisions like this really rapidly until we created a product that we could give to the early adopters.
Hi, this is a question for the third speaker. So you mentioned that during your training you used a safety algorithm, a safety controller, in case I expect the learning went terribly wrong. I was wondering, is this just a manual override that you were
yes,
deciding
it is.
when to apply?
Just
and
the emergency stop.
Okay, and how often did you, if ever, did you have to use that?
So we want to avoid high-speed crashing. So as long as the car hit the boundary, because the boundary are just a soft tube. As soon as the car hit the boundary, then we said, okay, this is a failure case. So we're going to hit the emergency stop. Yeah.
Right.
So we don't do it often, but we have to do it to avoid damage of the car.
So did it in the three rounds that you did? How many times did you have to intervene?
Okay, so in the video that you saw, we did not use it because this is after the 3 iterations of training. But in the early stage of training, we did use it. Yeah, and the car did crash.
Okay, thanks.
We have time for one more question. I think there's one in the back.
Hi, this is a question for the third speaker. Okay, I'm here.
I think over here in the back.
Yeah.
Okay.
All right. So I have a couple of questions. The first is, why could you not use the MPC expert at test time? Is it because it's slow, or is it because it's suboptimal? If it's suboptimal, then I'm wondering if you're using Dagger to imitate the expert, then your neural network policy cannot be better than the expert. You'll only be imitating the expert. So I'm just a little confused as to how the neural network policy can do better than the MPC expert.
Okay, I think that's a good question. First, the MPC is not optimal, it's always suboptimal, and we use it as an expert, and our goal is to achieve the expert performance. So we do not want the neural network to outperform it, we want the neural network to perform close as possible to the expert. The motivation was that if we use MPC to do the same task, then the computational load is very heavy. And we need to do optimization on the fly. We need to do planning and control on the fly. And also, it relies on more expensive sensors, such as GPS and IMU. But if we use a neural network that it only takes an image and wheel speed as input, the sensor cost is much, much lower than GPS and IMU. And the computational cost is also much lower. because we no longer need to do on-the-fly optimization in this case.
All right, so I think we'll close the session here in the interest of time. Let's thank all our speakers.